Hello, my name is Tony Lentz with FCT Assembly, and I am going to present how does printed solder paste volume affect solder joint reliability. This is a joint paper between FCT Assembly Solders, Jasbeer Bath, and Nihon Superior. First, I'll go over a brief introduction on what this paper is about and how we set up our experiment. Then we'll talk about the results of the data that we collected. And then from that, we've drawn some conclusions and have recommendations for volumes that would be required to create quality solder joints on a variety of components. And I've got some acknowledgments to thank the folks that helped out with this project. And this is a recording, obviously, so if you have questions, please send an email to my contact, which is shown at the beginning and at the end of this presentation. So solder paste volume varies pretty widely by stencil design. So in this case, we've got the stencil design for this PLCC 20 component. This is 100% volume, what the apertures look like, and this is the 30% volume stencil that we created. We shrank the aperture sizes and reduced the stencil thickness, and here's an overlay of those apertures lined up. So a pretty significant reduction in aperture size as well as stencil thickness to give that volume drop. And here are solder joints that were created from those two stencils. With the 100% volume, you can see wetting out to the edge of the pad and good wetting up on the component leads. Nice, well-formed solder joints. The 30% stencil volume, there's not enough solder to flow all the way to the end of that copper OSP coated pad, but there is wetting evident, and then the solder does wet the lead, but not quite as high as the 100%. Now these volume variations are common for a wide array of components. It's standard practice to make reductions in solder paste volume to enhance printability and to reduce the potential for float and skew, especially with bottom terminated components like QFNs. But this begs the question of what's the lower limit of volume? How low can we go and still achieve quality solder joint? So the question is, this reduction in solder paste volume that is normally applied to the stencil design, this occurs for a variety of components, but the question is, how does that affect solder joint reliability? So is there a volume at which is too low and will create a crack in a solder joint like this, or perhaps if there's a volume that is too high, that might create some other type of quality problem with the solder joints? So here's how we set up our experiment in order to measure and take data on this concept. We used this test board from Practical Components. This is coated with an OSP high temperature surface finish, and it has a variety of different sizes of components on it. We placed 4 SO14s here on the corners. We placed 2 PLCC 20s in the center, and then 4 SOT23s here in the upper left corner. And then along the bottom here, we placed a variety of sizes of passive chip type components, ranging in size from 1206 down to 0402. We made 7 different stencil designs for this project. We started off with the 100% stencil, which was, we took the data as supplied and as recommended by the component manufacturer, and just produced a stencil as is with a 4 mil thickness. We increased that to 125% volume by enlarging the apertures but keeping the same stencil thickness. And then we took that 100% design and reduced it to 75% solder paste volume by reducing the thickness from 4 mils to 3 mils. And then we again reduced the thickness down to 2 mils to give us 50% target volume. And then from that stencil, we reduced aperture sizes to get 40%, 30%, 25% volume levels. The material that we used for this was fine grained stainless steel with no nano coatings. Now when we took a look at the area ratios of the apertures for this design, they ranged from 0.83 up to over 3.0. So the area ratios were plenty large enough to allow for complete printing of the solder paste. Here are the print parameters that we used, and the solder paste that we used was a no clean sac type 4, and that's classified as an ROL0 type solder paste. Here's the reflow profile that we used for these test boards. We made a linear ramp to peak type profile for SAC 305 alloy. And the profile parameters that we measured are shown here on the right. Reflow was conducted in a 10-zone convection oven with an air atmosphere. Here's the actual process that we used to create the test boards and the data that we collected from those. So we printed 10 boards per variation. We cleaned after number 5, cleaned the underside of the stencil. Then we measured solder paste volumes. We placed the components and reflowed the circuit boards. We took pictures of the solder joints and conducted inspection for quality of the solder joints. We had pull and shear testing done on boards number 1 through 4. Board number 5 was used for cross-sectioning of the solder joints. Then we put boards 6 through 10 through thermal cycling. Then we did pull and shear testing on boards 6 through 9, and board 10 was used for cross-sectioning then after thermal cycling. We repeated this for 7 different stencil volumes with 10 boards created for each stencil volume. Then the data that we gathered out of that in terms of printing was we measured solder paste volume and calculated transfer efficiency percentage. Reflowed solder joint quality was inspected, and we tallied up the soldering defects. The shear and pull data was collected, shear data for passive components, the pull data for the leaded components. And then in terms of cross sections, we were looking for solder wetting, intermetallic thicknesses were measured, and some EDX analysis was done to characterize the intermetallics that were formed in the solder joints. Here's the thermal cycling profile that was used. The temperature range was -40 to 125 C. The ramp time was 5 minutes with a 10-minute dwell, and we conducted 1,000 cycles of thermal cycling. And then the shear and pull parameters are shown in the table below. Here are the results for solder paste volume and transfer efficiency. So here's the target solder paste volumes for each component and each stencil volume shown across the top. These are all in cubic mils of target volume. Here's the measured mean solder paste volumes for each component and each stencil volume. And then we converted those over to transfer efficiency numbers. So these are the measured transfer efficiencies based on the 100% volume stencil. So we took the 100% as a baseline, and what we did is we calculated these transfer efficiencies with respect to that in order to determine if they were matching our target volumes here. So for example, for the 25% stencil, we were actually getting anywhere between 25 and 34% solder paste volume. For the 30% stencil, we were actually getting 31 to about 41 solder paste volume, and so on. And if you look up here at the 100% stencil, these range from 110 to 122%. And for the 125%, even higher than that, we had volumes ranging from 187 down to about 138. So overall, we're getting higher printed solder paste volumes than what was targeted based on the stencils. And that's okay, because we're going to correlate all of our shear and pull strength data to the actual measured volume levels rather than to these target numbers across the top. So we're correlating to the measured volumes. And we did get a range of measured volumes, which was the goal here for this whole experiment. Here are the results for solder joint inspection. So here's the different component types and then the different stencil volumes. You can see the 25% volume stencil is missing from this table, and that's because the 25% stencil volume just didn't have enough solder to create a quality solder joint, so it failed visual inspection. So we didn't bother taking pictures or doing any further testing on the 25% stencil volume. Now if you look at the 30% stencil volume, you can see wetting on the component lead and wetting on the pad, but it certainly doesn't spread all the way to the ends of the pads on any of these components. 40%, there's some copper OSP showing on the board pads. By 50%, you've pretty much got complete wetting to the ends of the pads, and you can see the solder joints are a little higher up on the component leads, and so on. As you get up to the 125%, like here, you've got pretty much a straight ramp of solder going from the top of the component down to the board pad. And then for the leaded components, you can see a pretty generously formed fillets here. Now the 40% stencil volume in the SOT23s is missing because we were unable to place those components on those particular test boards, so we weren't able to gather any data on that particular combination. Here are the solder joint defects that were tallied up per IPCA 610 and J Standard 001 criteria. So here's the stencil volumes that we were testing, and here's the different components across the top. First of all, the SO14s had 0 defects, so nothing was found wrong with those components. The SOT23s had 2 different kind of defects that showed up: missing components and solder balling. And this was random solder balling around the pads of the SOT23s. So missing was due to a couple of things. During component placement, sometimes the blow-off pressure was sufficient to move the SOT23s off the pads, and then during reflow they continued to shift and completely, basically dislodged off of the pads, so they were physically missing. And that missing percentage was a little higher for the lower solder paste volumes, and it decreased for the higher solder paste volumes. So this says that higher solder paste volume was able to hold those in place a little bit better. And then solder balling really wasn't a problem for the low stencil volumes, but it became a problem for the higher stencil volumes. PLCC20s had no defects. Now the 1206s through the 0402s all showed 2 different kinds of defects. They were showing MCB, which is midship beading, which is shown down here. You can see a nice example of what the midship beads look like. And then also SKOP, which is my abbreviation for skew off pad. And so with the 1206s, there wasn't much skew, but there was certainly midship beading going on. The midship beading was relatively low at the low stencil volumes, and it got much higher with the higher stencil volumes, such that at 125% volume, every component had midship beads. The 0805 showed the same trend: very low midship beading with the low volumes, and it increased with higher volumes, and no skew was going on. 0603 showed the same trend. The 0402s, very little midship beading, except for at the highest stencil volumes. And then skew off pad was the problem with the 0402s. Those were small enough where they were skewing during placement in some cases, and in some cases they were skewing during reflow. And in either case, like the lower paste volumes showed more skew than the higher paste volumes. So more paste would help to prevent this problem for those type of components. Here's our shear and pull strength results. This is for the as received boards before thermal cycling. So what you've got is shear or pull strength in newtons here on the y-axis, and then the different component types across the x-axis. So what's missing here is the SOT23s. The SOT23 data was not very repeatable from one board combination to the next, and so it didn't make sense to include it here. But you can see, just generally speaking, the 1206 shear strength increased with increasing volume. So the volumes are shown by the different colored bars. The blue bar is 30%, 40, 50, 75, 100, and 125 is the light green bar here on the right. 0805 showed the same trend, generally increasing shear strength with more solder volume. 0603s and 0402s showed the same trend, but obviously these trends are a little flatter, so there's less of a difference in shear strength from the lowest volume stencil to the highest volume stencil. Now the PLCC20s and the SO14s did not show that trend, which is a little confusing to me. I assumed these would follow the same kind of trend as the chip components, but the pull strength was very flat regardless of stencil volume here for those lead components. Here's the shear and pull strength after thermal cycling. So you got the same trend here. 1206s increasing, 0805s increasing, 603s and 0402s. And what we see here is that the PLCC20s and SO14s assume the same trend. After thermal cycling, now they have increasing pull strength with increasing solder volume. But what we were looking for here was some kind of a severe drop in shear or pull strength, especially after thermal cycling. We were hoping that maybe the low stencil volume would have a big drop from the higher stencil volumes. And there is some differences here. With the 1206s, let's say you've got 38 newtons versus 50 newtons and 57 newtons. So there is a pretty big difference between the lowest and the highest. But the question is, where's the pass-fail limit? Where would you draw a line through this data and say that shear strength is too low and that shear strength is high enough? That's the question. So there wasn't a real clear indication here. Here's cross-section results for the chip component. So here's the different stencil volumes across the top, and then the different components here down the y-axis. These cross sections, just generally speaking, you can see good wetting to both the pad and the component lead, and then that wetting and spread just improves as you increase solder paste volume. Same thing is true for, say, the 0805s and 1206s. All of these look pretty good. I don't see anything wrong with these cross sections. Here's the cross sections after thermal cycling. Very similar to what I just showed. The thermal cycling didn't change the shape of the solder joints because we weren't remelting the solder. So the solder joints didn't really move around at all as you would expect. Here's the EDX analysis for the board pad intermetallic. So this is at the board pad interface where we're soldering to a copper OSP finish. We found copper, carbon, copper, and tin. Carbon's always present in these SEMs just due to natural contamination. But the copper and tin were found in a ratio that would represent the CU6SN5 intermetallic. Here's the EDX analysis on the component intermetallic. So at the component lead interface, there's a nickel barrier layer on the component, and then that's next to the copper tin intermetallic layer here. And that's because the components did have nickel as part of the finish on the leads. Here's intermetallic thickness measurements on the as received boards. I just picked the smallest chip component, the 0402s, and then the largest, the 1206s. And the B means the board pad interface, and the C means the component lead interface, and then the different stencil volumes again are across the top. So you see the 0402 at the board pad ranges from 2.4 to 2.6 microns roughly, but it doesn't change much with volume. So solder paste volume really didn't affect the intermetallic thickness. The same thing is generally true for the component lead interface. You got 1.7, 1.9, 2.0, 1.5, so there's no trend here in intermetallic thickness with solder volume. The same thing's true for the 1206s. Here's the intermetallic thicknesses measured after thermal cycling. Generally speaking, all of these increased with thermal cycling, but again, there's no difference really between 30% and 75% and 125%. There's no trend in this intermetallic thickness with solder volume. Same thing's true for the 1206s across the board. Here's a chart showing the intermetallic thickness change with thermal cycling for the different chip components. So here's the change in intermetallic thickness, or the difference basically between after thermal cycling and before thermal cycling. The different stencil volumes / components are shown below. You got 30%, 40%, 50%, 75, and 100, 125, and then the 4 different components are broken out with each one. Generally speaking, you've got most of these are an increase in thickness, as you would expect. There are a few decreases, and those are just anomalies in the data due to the components that we picked maybe had different intermetallic thicknesses based on just that cross-section. And if you did more cross-sectioning, I'm sure you'd see overall an increase in intermetallic thickness change. But the mean change here was an increase of 0.34 microns. Here's cross-sections of the lead frame components. So here you've got the stencil volumes across the top, PLCC 20 as received and after thermal cycling, and the SO14 as received and after thermal cycling. Again, thermal cycling didn't change the shape of the solder joint, but what I see here is that with the 30% stencil volume and maybe the 40% stencil volume, the wetting on these leads maybe isn't quite up to par. It's not quite up to standard. I mean, you see wetting evident, but on the toe especially, it looks very low in terms of thickness with these 2 volumes. And then you go to 50% and higher, and that improves. Here's the intermetallic thickness measurements on the lead frame components as received. Once again, increasing stencil volume from left to right doesn't seem to change these thickness measurements very much. Same thing with the SO14s. I mean, you start with 2.6, 2.7, 2.4, 2.7, 2.0. So intermetallic thickness again is not affected by these solder volumes. Here's the same data after thermal cycling. Same trends are seen. Once again, all these measurements are a little thicker after thermocycling than they were before thermocycling. And here's a chart showing those intermetallic thickness changes again for the lead frame components. All of these are pretty much increases in intermetallic thickness. The mean overall change in this case was 0.41 micron increase with thermocycling. Here are the results of solder joint strength and how they correlate to transfer efficiency. So here's the passive chip components, the 1206s, 0805s, 0603s, and 0402s. Transfer efficiencies across the x-axis and shear strength on the y. And then the blue line is as received and the orange line is thermally cycled. So you've generally got an increase in shear strength with increasing transfer efficiency like we showed before. And the trend here is actually sort of a linear relationship. And basically you can also clearly see that thermocycling decreases that strength significantly. Same thing's true of the 0805s, 0603s, and 0402s. The biggest drop in shear strength was shown for the 1206s with thermocycling, while the others dropped a lot less. Here's the pull strength with the lead frame components versus transfer efficiency. So again, you got transfer efficiency here. The blue is as received, so with the PLCC20, the as received components had a pretty flat pull strength that didn't change much with volume. But after thermocycling, it did. It had a linear increase. And the SO14 actually showed a decrease in transfer efficiency with increasing solder paste volumes. But then after thermocycling, it changed to more of a linear increasing relationship as you would expect. Here's a summary of all that data. So here are the different stencil volumes that we tested, the visual inspection of the solder joints, the solder defects that we found, the cross-sectional data, and the joint strength data. So the 25% stencil failed visual inspection. There wasn't enough solder to create proper solder joints, so we didn't do any additional testing on that. The 30% stencil volume through 125 all passed visual inspection of the solder joints, generally speaking. So if you were just going by visual inspection criteria, you could essentially use stencil volumes ranging from 30 to 125% on these types of components. But there were defects, and the defects that we found were missing and skewed components here with the lower volumes, and then we started seeing mid-chip beating with the higher volumes, especially on the passive chip components. That could be corrected, however. Mid-chip beating, of course, you could repair it. You could change the stencil design to remove some solder paste from under the body of the component to correct that. And then in terms of cross-sectioning, the 30% stencil volume was not okay for the leaded components. It was too low. But 40% and higher, the cross-sections showed good wetting. I mean, the solder joints look well formed. And then in terms of joint strength, we drew our own conclusions from all the joint strength tests. Like I said earlier, there wasn't a clear drop-off in the data, but we had to put a line through that data somewhere. So the 30% and the 40% stencil volumes were too low, in our opinion. They gave joint strengths that were a little bit too low and may not be reliable over the longevity of that electronic assembly. And 50% and higher, however, did give joint strengths that were acceptable. And we declared acceptability based on our data, but also based on other work. We were comparing those to other papers that have been published previously to look for comparable data. So here are our conclusions and recommendations we can make from this experiment. So here's the different components again. Here's the transfer efficiency we'd recommend for acceptable solder joints and the transfer efficiency for reliable solder joints. So for the 0402s and 0603s, it's 50% for each one. For the 0805s and 1206s, it's 30% for acceptable visual inspection, 50% for reliability purposes. PLCC20s and SO14s, we chose 40% for each one of these levels. In the SOT23s, we chose 75% for the acceptable solder joints, but we didn't get very good data out of the pull strength testing, so we would say more data is needed to establish a TE for reliability. Now, we had comparable data for most of these components except for the PLCC20s and the SO14s. So those numbers are based strictly on the data that we gathered in this work. Here are our recommendations. So a wide range of solder paste volumes gave acceptable solder joints, but if the volume was too low, we started seeing what might become reliability issues. 50% solder paste volume was acceptable for passive chip components, and 40% was acceptable for the PLCC20s and the SO14s. But we would advise PCB assemblers to create their own standards for solder paste volume based on the requirements on the types of components that they're using and requirements from their customers. We would like to acknowledge the help of Nihon Superior, Mr. Tetsuro Nishimura, Mr. Yuji Kozutsumi, Mr. Keith Howell, who provided the lab facilities to do all the thermal cycling testing, the solder joint strength testing. They did all the cross-sectioning and helped with some of the data analysis. I'd also like to acknowledge the contribution of Mr. Greg Smith, Blue Ring Stencils, who provided the stencil designs and also assisted with the PCB assembly and inspection processes. Thank you for listening to this presentation. I hope you got something valuable out of it. Again, if you have any questions, please email us at the email addresses below. I'm probably the best contact, so you can reach me here at tlentz@fctassembly.com. Thank you again and have a great day.